This is our third reverse chain rule video, and it has a little bit of a trick to it that the others didn't have. It's going to use that step number 4 that was listed in our original steps for how to find a reverse chain rule answer. Before we do that, I want to just remind you of the hopefully obvious, which is that when I say sine squared x, it really means sine x is being squared. So I remind you of that just because it makes it a little bit easier for us to remember what it is that that we have for an inside function. So when I look at this problem and say which function in this question is inside of something else, we say sine x. Sine x is inside of the function x squared. And then we go ahead and fill in the rest of the table, so that's step number 3, and say the derivative of sine x is cosine x. The antiderivative of x squared would be 1/3 x to the third. And I'm going to just check and make sure that this matches with the way the format is supposed to be. So let's look here and see what we have. We've got the inside function g, well that's the sine of x, inside the derivative of f, which is x squared. Well, that I've got right here. That's the inside function g, sine of x, inside of x squared. And then we're supposed to have multiplied by the derivative of g, which we've got, multiplied by cosine, so that is there also. But what's bizarre is this 12, because it's nowhere in my little table. I don't have a 12. So all we have to do is remember what we want. What we want is this form right here of the integral, the one that looks like the reverse chain rule. So what I would really like to see is the integral of the sine of x squared multiplied by the cosine of x dx. That's what I would like, because then I would have exactly the right pieces. G plugged into the derivative of f, multiplied by the derivative of g, and it would all be fine. Well, that's not exactly what the question says, though. So all I need to remember is that it's absolutely okay to take a constant multiplier, like that 12, and put it out in front of the integral. That's absolutely all right. If you are multiplying by a constant, it can be inside the integral or outside the integral. It doesn't matter. So to find my answer to this question, I just need to remember that the 12 here, this constant multiplier, has to be multiplied by f of g, plus some constant on the end. But this part, f of g right here, we're talking about finding this integral. And this integral is found by doing f of g plus c. So it all just goes back to the easier reverse chain rule questions. So the piece that I'm going to put inside here is g plugged into the f function, 1/3 sine of x cubed. And that's my answer. It would be nice if we took an extra step and made it a little prettier. So 12 multiplied by 1/3 is 4. So we could say 4 sine cubed x plus a constant would be the nicest way to write our answer. And if that is something that you're shaky on in the beginning as you're getting used to this, you can always check your answer to see if it works. I mean, we could just do chain rule here. So if we were to just do the regular chain rule, we could check our answer and say, is it true that the derivative of 4 sine cubed x is 12 sine squared x cosine x? And if we did chain rule, it actually would work out, because my inside function is the sine of x. It is inside of 4x squared. Now remember, we're doing the regular chain rule now. We're taking the derivative of this answer to see if it works. So, oops, sorry, that's 4x to the third, not squared. 4x to the third has a derivative of 12x squared. Sine has a derivative of cosine. And chain rule says that you take g, put it into the derivative of f, and multiply by the derivative of g. Well, sure enough, that was the original question, 12 multiplied by the sine of x multiplied by cosine. So check, we know that we did it correctly. So you don't need to do that check every time, but it might help you in the beginning as you get more comfortable with reverse chain rule, just to go back and remember that we really are just working backwards.